So today we're going to talk about strains. Strains is very similar to stresses in their treatment. However, strains help us determine the deformation of a structure. So let's get started. So consider the following. I can have, let's define the state of strain in the following way. E is equal to E of xx, E of xy, E of xz, symmetric, so I'm only going to write the diagonal terms, yz, ezz, and remember, this is a symmetric matrix. What tensor, technically speaking. Now, writing this in the terms that we are used to having the engineering strain, where this is actually 1/2 of gamma, then you can rewrite this expression as exx 1/2 gamma xy 1/2 gamma xz eyy 1/2 gamma yz ezz. Okay, so another thing that you have to keep in mind when you work with strains is before I move, the whole idea of the state of strain, this is a state of strain. The whole idea for having a state of strain is to find the principal strains. Okay. What we also know is from your strength of materials, how do we find the strains, right? If you remember our chart, don't forget your chart that said external loads, internal loads, stresses, and strains. And then you also had displacement. So basically, we have done this. We will do this in the next few classes, if not today. And then we are here. Okay, this is where we at today. We got the stresses, given stresses, how do I find my strains? If you remember from your mechanics of materials textbook, you use what you call your famous Hooke's law. Now, Hooke's law is only valid for, it comes under the assumption that this is a linear elastic. Okay? When I talk about linear elastic, what am I really talking about? I am talking about the following. I am saying you can have a problem in which it's completely linear. So you're saying your material behaves from here to here only. This is linear elastic because your curve is linear and it's elastic. Typically, we say it's elastic if it's below your sigma yield. Now, you also can have nonlinear elastic. Could be a good case where this is still the corresponding is yield. So this is nonlinear elastic. And materials like aluminum or steel especially, they tend to have a curve that looks something like this. So in their curve, this is a point over here. This is sigma yield. So anything beyond this point will become plastic. So what you're basically saying is that once you apply your load and it goes beyond this point, there's going to be a permanent deformation in your structure. Okay. We design in engineering, we want to stay typically, unless you're told otherwise with the program that you're working on, in the elastic region. This is the region that we always want to stay. We like elastic. Elastic because we know what sigma yield is and how that works, and it's easy to relate one thing with the other. Now, given the stresses, how do I find my strains? That's the next question. That is very easy, and you can do that by using the equation 3.19 of your textbook. You can pause right now and you can write these equations, but I'm sure that these equations will be familiar to you. This is nothing else than the Hooke's law, also known as the Hooke's law. And also you have to know that your G, that's your shear modulus, is E divided 2 times 1 plus nu. Easy way to remember this, a small secret, if you have EX here, then you have an X here, then here goes everything else. You see, you got a Y, then you have a Y, then you have Z, you have Z, and then this is Poisson's ratio and everything else goes there. If you want to keep this in the notation that I am using, when I'm doing these exercises or I am writing, I typically tend to write EXX, but that's what small x, this is their notation. And their notation, instead of I write sigma XX, they write a simple x minus nu sigma YY plus sigma ZZ. So if you're going to write in your notes, you're welcome to write it like this, or you're welcome to write it like this. And the same thing, it goes on. So that is important. So that means that if I know my stresses, I can find my strains. If I know my strains, I can find my stresses. And so there is a very nice equation that you have to know that's only valid for isotropic materials. Only for isotropic materials. Only for isotropic materials. Okay. If I have a state of stress, okay, so you have this state of stress, it's fully loaded, and then from the state of stress, you find your principal state of stress, okay? So this principal state of stress corresponds to this state of stress. So this is 10, let's say this is sigma 1, 0, 0, 0, sigma 2, 0, 0, 0, sigma 3. And so you have your principal stresses. And what I can do is, I have two ways to do this. I can go from here directly, I can find what my principal strains are by using Hooke's law. So I can say this is E1, 0, 0, 0, E2, 0, 0, 0, E3, where E1 is nothing else than 1 over this sigma 1 minus nu sigma 2 plus sigma 3. You can see how easy this is, right? This is 1, 1, and rest goes there. Sigma 2 is 1 over E sigma 2 minus nu sigma 1 plus sigma 3. and then let me write sigma 3 here. E3 will be 1 over E sigma 3 minus nu sigma 2 plus sigma 3, and everything else is 0, okay? So this is only applicable when this is for isotropic materials. For any other type of materials, if I wanted to find my status, this is a lot easier to do it like that, actually. If I wanted to, and vice versa, right? I can also go for isotropic, again, only isotropic. Only isotropic. If I had a statosstrain, right? I can find my principal statosstrain from here, and then from here I can find my statostress directly from here, okay? So that is also possible. Now, if you were to do this in the general sense, right, for a general material that's not necessarily isotropic, but it applies to isotropic, okay, for a general material, what you will have is, if you have this statostress, okay, from the statostress you find your statostrain, okay, and from your statostrain you find your principal strains, and from your statostress you find your principal stresses. This is always applicable. It doesn't matter the material. Always true. Just if you're working with isotropic material, it becomes a lot easier and simpler just to do this. Okay. Now, you have a nice Matlab code that actually does this for you. Let me pull the Matlab code and let me show you what the Matlab code does. So in your Matlab code, if you run here, you start, let me close everything here. You don't need any of this. So you open principal strains. This code is just like your principal stresses, but does principal strains. So when you run this code, it's going to ask you for, again, if you're working in inches. This doesn't really matter. You can put whatever you want. Just give me a sec. Okay, the problem is fixed. So you just enter the values. Strains are typically given in microns. So let's suppose this is 2 microns, 1 micron, 3 micron. Just don't forget this is divided by 2. Okay, if you don't divide by 2, you're going to get an error. So let's suppose this is minus 0.05, this is 0, this is 0, and your problem basically tells you this is in radians and gives you the Mohr circle. As you can see, this is what you get for the Mohr circle. I just enter arbitrary values here, which obviously do not make any sense. One of the values had to be on this side. This is just to show you how it works, to give you an idea. And so this is also available on the principal strains and is on your website. And also we have one for the Hooke's law, but I will discuss that as we do the example. The next two example, one example how to do the principal strains, another example how to do principal stresses. The principal strains given stresses.